Okay, so as we've heard, so thanks a lot for the organizers for inviting me to talk. So as we've heard from Matt in the previous talk, the PCP theorem looks like, the quantum PCP theorem looks like a really complicated thing to prove. I want to state here the classical PCP theorem in a different way. Even though you don't really have, for those of you who haven't seen it, you don't have to remember, you don't need to understand it really, but I just want it to be written here in a different way so that I can somehow refer to this intuitively. So what does the PCP theorem say? It's probabilistically checkable proofs. It says something like that. It says there is a way to map, there's an efficient way to start from from a given problem, say a set of local constraints, to which the solutions are given in some way in coding, say the assignment for some formula, x1 equals 0, x2 equals 1, etc. There's a way to map this to a different format in which the set of constraints is just slightly larger and the solutions are given in a slightly different and slightly longer format. Such that, well, if you look at the first problem, the first, where we start with, well, a set of constraints is either satisfied or not satisfied. Okay, so I can decide whether there exists a solution to the set of constraints or there doesn't exist. So there's one constraint which is violated. Okay, so in the new format, either there exists a solution or all suggested solutions violate at least 10% of the constraints. That's what the PCP theorem says. Okay? Which is really, if you haven't seen it, it's a really remarkable theorem. Because it says that there's some kind of robustness in the way we can encode NP-hard problems, which is, if you think of, for example, an NP problem as a mathematical theorem and your solution is a proof, then this says that you can write down a proof in a way which you can check whether it's correct by just reading a small number of bits from it. Because if 10% of the constraints are violated in case the theorem is incorrect, then you can just pick a random constraint and condition on whether it's violated or not, I can decide if the theorem is correct, if the proof is correct or not. With probability, with a constant probability. So that's really remarkable. Okay, and Matt said this is the best contribution that computer science has given physics. Well, I think it's the best contribution that computer science has given anyone in the past few tens of years. It's really an amazing theorem. What?
No, but I mean the practical contributions that computer science has made are quite relevant.
They are practical.
Okay.
You know, actually they're trying to make it practical. The PCP theorem. It's not yet there, but it does have a lot of practical implications. So
people write their papers in a different way with a lot of practical. I just check order 1 bits of the paper and I see if it's correct or not.
Okay, so anyway, if you're interested in the history of this PCP theorem, so the thing is that it didn't just, the way it was proven, it wasn't that, several people just got into a room and decided, well, we're going to prove this amazing theorem, and out came this theorem. What happened was, it was a remarkable, at least the way I view it, is some kind of a random walk between really beautiful ideas that nobody really had any sense that it would lead to this theorem. They were just playing with various different ideas like program checking and local testability of various properties and stuff like, so things that didn't seem to be leading, and interactive proofs, things that didn't seem to be even remotely related to this, and combining all these things, out came this remarkable theorem. So if you're interested, you can read this beautiful account of the history, or rather a history of the PCP theorem. Like any really major enterprise does not have one history. So this is a history of the PCP theorem by Ryan O'Donnell, really recommended reading of this sequence of events. So really, if we're trying to prove a quantum PCP theorem, maybe the right way to do is not to try to prove it directly, but to see whether we can sort of start with some toy problems. Maybe look at for inspiration at the toy problems that those people who led to this remarkable theorem started to play with, and see whether these ideas have any meaning in the quantum world. So if you see this formulation of the PCP theorem, really one much simpler way, much simpler thing that is happening here is a much simpler question. What properties can be tested globally? What kind of global properties can be tested by just probing locally a string of bits, by just reading a small number of bits? Okay, so I want to give an example of this, but really this is the question that I want to be asking. What global properties can be tested locally? And then I want to borrow this to the quantum world. Okay, so...
But locally just mean order 1 bits, not geometric or anything.
I don't want to be specific here, but right now locally means order 1 bits, maybe just a much smaller number of bits than the actual string. Okay, so let's look at an example that was really very influential in the classical story of the PCP. So this is linearity testing. Okay, so what's linearity testing? Suppose you have a string like this, which is claimed to be the evaluation of a linear function. So it's a function from n bits to 1 bit. And if it's a linear function, it's very easy to see that there is a string of n bits a such that fa of x equals to a dot x, sum over ai xi modulo 2. Okay, so this is if and only if the function is linear, meaning that f of x plus f of y equals to f plus y, where plus is everywhere, coordinate-wise modulo 2. Okay? So now suppose this is the property. I'm given a string like this, and I just want to ask whether this string has the property that it is the table of a linear function. That's the property. So this is the question, and of course I cannot answer this question by just probing a constant number of bits, because I can take a linear function and change it by 1 bit, and it will not be a linear function, but I will not be able to detect it randomly by picking a small number of bits, right? So this property is not testable locally if I'm just asking really whether it's in the linear functions or right outside. However, if I'm doing this trade-off between accuracy and efficiency, and I don't ask really if the linear function is, if the function is linear or not linear, but what I'm asking is some kind of an approximation. I'm asking, is a function linear or is it far from any linear function? Far, I mean the number of bits you need to flip is, say, linear. It's a fraction of the total number of bits. Okay, so this is my question. Am I in the property or far from it? And then it turns out, okay, so that's the question. And then it turns out that in this case, it's really easy to detect whether I'm far from the property or within it.
What does far mean?
So far means that if I have a given string, then the number of bits that I have, the Hamming distance, or the number of bits I have to flip in order to get into the set, meaning in order to get the linear function for some a, this number is a fraction of the length of the string, a constant fraction. Okay, so okay, so there's this theorem by Blam. Sure.
I'm a little confused about the setup. So what is it that when you say you're going to test locally? What are you going to test? What are you going to ask, or what do you get?
So this question is not good because linear or just not linear is not the question that I'm going to ask. So really, the question that I'm asking is this: is f linear or is it far from any linear function?
And what information are you going to use?
Okay, so what I'm given is access to this string, but actually what I'm given is ability to pick, say, a constant number of bits randomly from that string and read them.
So could you tell me again what the encoding of the string is?
Oh, the string is just the evaluation. This is the table of the function fa for some given a. So this is fa of the first string, 0000 n bits. This is fa of 0001. This is fa of 00010, etc. So it's just a table of f, and I can probe it in a constant number of places, and then I need to decide if it's linear or not, or far from linear. And it's a beautiful theorem by Blum, Luby, and Rubenfeld that says that yes, if I just pick sort of just three locations here randomly, then I can decide, meaning, okay, so here's the test. What I do is I pick a location x randomly, that's an n-bit string, a location y randomly, and then I also probe the string at the place x XOR y. So XOR is just addition modulo 2 coordinate wise of the two strings. So, and I'm testing whether f of x, I'm just checking whether f of x XOR f of y equals f of x XOR y. Right? So if it's a linear function, it should satisfy this. So if f is a linear function, it passes the test. And the point is that if f is delta far from linear, meaning that a fraction delta of the locations need to be changed in order to make it linear, then this test fails with probability larger than delta. Okay? So, okay. Okay, so let's just, I think it's easier for this audience to think about it as a code. Okay, we have our property, the set of linear functions, can be viewed as a linear subspace. You can also see it as the space spanned by all rows in a Hadamard matrix acting on n qubits. Okay, so if you switch 0 to 1 and 1 to -1, if you do this mapping, then addition becomes multiplication, and this set of function is just the strings of the rows of the Hadamard matrix. So this is a subspace. And then we have three local constraints on this subspace. So for all x and y, we have a three local constraint at x, y, and x XOR y. And this defines sort of a Hamiltonian, okay, over all possible such triplets. And then the random constraint looks like this. So we require that this happens. And so the test is the given word in the code, in the subspace, or far from it, which is delta far means that what we require is that if it's far, then the number of violations, the number of constraints that are violated, divided by the total number of constraints, is at least some constant. Okay, so what does this mean in physical language? It means that if there are many, many errors, then the energy in this Hamiltonian is large. Okay? Yeah, so is this, okay. So, okay, so this idea can be extended. So this question is actually a very fundamental question. What kind of properties can be, what kind of global properties, like being in some subspace, some simple subspace, can be tested to within good probability by probing a constant number of locations in the string. So by just looking at a very, very small part of the string. Okay, so this is really, this can be taken to various directions and has been taken to various directions in computer science. It's really instrumental. So it started with program checking. So it is tightly related to the question of whether a given program, a computer program, behaves as it should behave. It's related to the notion of property testing, which does not necessarily have to do with linear subspaces. You can also ask how far am I from, so you're given a graph, how far is it from being three-colorable? I don't know. You can talk about various properties. not necessarily linear subspaces. It's instrumental in probabilistically checkable proofs. So locally testable, so all probabilistically checkable proofs, all proofs of the PCP theorem use this notion of locally testable codes. So codes such that you can test that they're defined by local constraints, and such that by picking a random constraint, you can detect that with good probability, with constant probability, that a word is far from the code. Okay, so such are the example is the Aharonov code, low degree polynomials, Rigg-Muller code. Never mind the names, but this is really, it goes in various directions. So really the question that I want to raise in this talk is what about locally testing global quantum properties? So can we locally, what kind of quantum properties, and I'm going to be slightly more precise in a minute, but what kind of quantum properties we can test, where quantum properties, I mean multi-particle properties that are really globally quantum, can we test by probing whatever the information locally, by not getting all the information, but just getting a very small part of it. Now, this problem can be interpreted in two ways, and I'm going to talk in this talk about both of them. So the first is you can ask what kind of properties can be tested if you're given a quantum state, and what you're doing is you're probing a small number of qubits of this state. Okay, so that's the question. That's the first question you could ask. You can also ask, if I'm thinking about classical encodings of quantum objects, then what happens? Are there interesting things that I can say in that respect? Okay, so I want to look at this problem, at this question. Yeah.
So it was crucial in classical property testing that you had this notion of distance. The positive instances, the negative instances were separated away by some Hamming distance from the positive instances. And so what would correspond to that in the quantum setting? So when you are testing, you are not really testing, well, as you said, that you are not testing whether it's positive or not, but whether it's positive or very far from positive.
Right. Okay, let me answer this through this slide. So here is a possible. So let me start with asking about so testing quantum properties by accessing quantum states. Okay. So then the first analog to what we've seen would be quantum error correcting codes, which can be locally tested. So let's see what that means. So I have a Hamiltonian, which is a sum of local terms, and the quantum error correcting code would be the ground space of this Hamiltonian. And for this code to be locally testable, what I would require is that first, if psi is in the ground space, then obviously the energy is 0, but this also corresponds to the probability that I would reject if I tried to measure, if I write H as a sum over Hi, then psi H psi over M is sum over 1 over M, sum over psi Hi, psi I goes from 1 to M over all constraints. So this thing can be viewed, if Hi is a projection, as the probability for this state to violate this constraint. Okay? So this is basically your rejection probability if you randomly pick a constraint and check it. So we want, the right analog would be that this probability is 0, so the energy is 0. Or if psi is delta far, and I'm going to answer Mario's question in a moment, if psi is delta far from the ground space, then I want the energy, the density of the energy, meaning the energy divided by the number of constraints, to be at least some constant. Okay, epsilon as a function of delta. And I call this the soundness. Okay, so what does it mean to be delta far? So what we mean is something which is which we've learned from the study of quantum codes. It's the same thing. So you can talk about Hamming distance also in the quantum world, where what you want is that your state would be delta far from the code if for any operation that acts only on delta n qubits, you will get zero intersection with the code, zero inner product on the code.
I'm sorry, Dorit, but you already have a definition of distance here without going to defining it in terms of Hamming distance. In the sense that this already says, you define the local Hamiltonian, it gives you a notion of distance. You're either in the ground space. Your promise is you're either in the ground space or delta far.
What
now
is delta
all you
far?
need to delta far in terms of those terms of the Hamiltonian.
Oh, no, sorry.
But you could define it this way, and that would be the natural analog.
No.
And then the only question would
No,
be,
it's
is
not
this an interesting ground
Sorry,
space?
it's not the natural analog.
Yeah.
It's not. Let me explain it again. In the linearity testing, there is the locations where I need to change,
Yeah.
and there is the number of constraints.
Yeah.
And the constraint correspond to the energy constraints,
Yeah.
and the locations of the error is a different thing. So let me give an example actually with the Dorit code, which will explain it better, I think. So here's.
Can I say something here?
Yeah, so this is a very, very important distinction between errors and the constraints that are being violated. And it could be, and I'll talk about this in a moment, it could very well be that you are very far from the code, but only very small number of constraints shout. And this is why BLR needed to work so hard. They talk about a state which is delta far in Hamming distance, and then they say the number of constraints, the probability to pick a constraint which is violated is large. So this is a connection between the errors in the string and the constraints that are violated. These are two different things.
Yeah, but what I meant was this, that in terms of what that interesting property is, it could be, you could have this notion of distance in terms of Hamming distance, but the property would be, well, it would be some property of this ground space versus everything far away. So in other words, there's this issue of how do you map an interesting property in there, distinguishing what's.
So Umesh, so the Coulomb-Rubin-Feld result is exactly interesting because there are two different notions for what it means far away.
Sure.
Like one is the far away in Hamming distance, and the other notion is far away in terms of like number of violations, and so that these two are related. These notions. So here we need two notions, right? So what would be the other notion? So one is
Okay.
Okay?
Yeah.
Is there still...
It's good, yeah.
Okay, so, it would be... So I think that maybe you're hinting to a possibility of defining a distance in a different way based on what would be interesting. And that is a good question. That's one, and I'll refer to that later on. Okay, so it's but for now, it's a natural choice of a distance to talk about Hamming distance, also in the quantum case. And we've learned from stabilizer codes that this is a very, very interesting notion. The entire theory of error correcting codes builds on this notion. So, for example, let's look at the Dorit code. So, for the Dorit code, you can have a string of errors along. So, the Dorit codes, like Matt explained last talk, you can have errors. So, the qubits are set on the edges, and you can have errors along, say, all the edges of this green line. But the point is that even though the distance of this error, of the resulting word from the code is actually, could be very large. It could be the length of the string here. So something like square root of n. The number of constraints that it validates is only 2. That's a string-like operator. It just validates the edges of the string. Right? So
I still don't understand how exactly do you define the analog of the Hamming weight. So you say on how many sites did an error occur? Because this might be that even though there were many errors, there was no logical error, right? And so then you won't be able to distinguish.
Right. So I think for this talk, the easiest to think about it is think of a stabilizer code, and the distance is really the length, the weight of the error modulo the centralizer of the group. Okay, so you don't take into account errors that are logical gates. These are not considered errors.
Is it well defined? I mean, how do you count how many errors happened when you do this modulo?
You just take the weight, the minimal weight modulo the centralizer of the group. Okay, so with the Tor code, you get something which is which has very bad behavior, right? It has only a very small number of constraints that are violated, and the length of the string is very large. Could be square root of n. And the same for the 4D Tor code. You can have an error which is something like an area, but the errors will be along the surface. So, okay, so this is connected, and some of you probably have already noticed that, to the notion of energy barrier. Yeah, so what's an energy barrier? So the energy barrier of the code is the following. It's if you're in a code and you want to move to a different word in the code or token onto it, the question is, how much energy do you need to invest in order to do that? Okay, so for example, in a Tor code, if you want to move to another code word, then it suffices to create just 2 defects, and then there's no energy cost for letting them just go around the circle. So basically, this is the landscape of the energy for the Tor code. So the energy barrier is a constant. And it's a very, very interesting question to come up with codes which have, the question of energy barrier is very interesting for physicists and also in quantum information, because of the connection to self-correcting memory and also self-correcting computation. So it is the assumption that if the energy barrier is large, then the system is sort of passively protected against errors. Okay, because the system wants to go to the low energy levels, and going up in the energy is prevented, and you need to do that in order to perform a logical gate. Yeah.
Right? You're talking about a particular basis in the ground space, is that right? Because when you're saying moving from side to side prime, isn't it?
Well, I'm talking about any word going to an orthogonal word.
That's true even if you allow linear combination?
Yeah, you just have local errors. But it doesn't need to be in the same basis.
You can't flip signs, like take A plus B and A minus B and get something local.
No, that's the point. You have to protect also against such things, because A plus B and A minus B would mean a logical gate, which is a Z or whatever. I don't know what the... Yeah, it would mean some logical gate, and that's not allowed. So the energy barrier prevents you from performing.
As long as you have 2 basis elements.
I'm sorry?
2 orthogonal basis elements, then A plus B and A minus B are close, right? Or not?
They're close, not... Okay, so you cannot move, for example, in order to... This is a logical gate, yeah? You're moving between 2 states, which encode 2 different states, 2 different logical states. So this is not something that I want to allow without paying a lot of energy. Maybe you're not understanding the question?
Maybe you want to say, like, imagine the energy is being measured along the way, something like that.
Yeah, but it's important that that the steps along this path act on order 1 qubits at a time. They don't have to act like in order to go to different eigenstate of the Hamiltonian or something, but they have to be local. And if you want to do any logical operator, then that it needs order the distance of the code qubits to act on. So, but I don't quite know what the question is.
I think I'm just confused. It'll resolve itself on its own.
So I think the best picture to have is the picture of stabilizer codes, and then in order to apply a logical gate is basically to write down x's or z's or whatever. So it's a product of Pauli's. So in order to apply such a string of x's, for example, you have to start by an x and then accumulate those x's around the line. So if you move between two states of okay, I don't know if that's helpful. Okay, so anyway, this is just essentially just a connection. It's not something that I want to get really into, but the point is that that it's clear that this energy barrier is somehow related to this notion of local testability. But okay, so Haas code in 3 dimension does have this energy barrier. So it created a lot of excitement, and I think we're going to hear a little bit about it tomorrow or the day after tomorrow, hopefully. But its energy barrier is logarithmic in the size of the string. So in terms of local testability, it doesn't work that well, because we want, again, it's log L divided by L. So we're not going to get any constant or any nice behavior. It's going to be some inverse polynomial. So it looks like, energy barrier is a much weaker requirement than LTC. First of all, because the energy barrier just requires that during the path we'll get to some large energy, whereas for LTC we want that whenever we get far away from the word, then we get large energy. That's one thing. And then for physicists, energy barrier which is macroscopic is sufficient. Whereas here, it's not sufficient, because if the energy is macroscopic, but say it's 1 over square root of n, then your probability of detecting it will be also 1 over square root of n. So it's not good. Okay, so it's so this goes in that direction, but doesn't look like it goes in that direction. Yes.
So I think what people are actually interested in is the free energy barrier. So there's an entropic contribution which is very, very important. But does it play any role here?
I don't know how to compare this to the free energy.
You also have to know how many states are around the state of interest somehow. So how the landscape of exit from one well to another.
Yeah, whether you have many possibilities to go out. I don't know. I haven't thought about it. That's a good question. Barbara, do you know how these compare?
Well,
when you...
yeah, but I mean, I think your comment was just that what you're interested in is different from the energy barrier. So
well, I want to say that
right?
they're
It's
related.
much stronger. Yeah, but I mean, you're never, if any finite dimensional code on a d-dimensional list, your requirement is never going to be fulfilled. If it's a fixed lattice d-dimension.
Well, it's not clear. Okay, let's.
No, you have to go to these kind of constructions. Because the dimensionality of these boundaries is always lower than the number of.
Yeah, but it's not clear that you only have codes with dimensions. Okay, so
no, I mean, if I'm just saying if it's a d-dimensional lattice and it's local interactions, then we have a bound on the distance can scale, and that tells you.
I'll get to this. I'll get to this question.
Geometries, it's different. I'm not saying.
Okay, I'll get to this question. I don't know.
Yeah.
Okay. Okay, so it looks difficult to construct such locally testable codes, and there are other natural candidates that one might think about, like take classical locally testable codes like the Reed-Miller codes, if anyone is familiar here with those, and construct quantum Reed-Miller codes, which are the CSS version of classical Reed-Miller codes. But then they won't satisfy. They won't be good either, because one of them, the dual or the primal, will have bad local testability. So if you didn't understand this, forget about it. But that also, essentially the bottom line is we don't know of codes that behave well in terms of this local testability. Yeah?
Sort of answer is, I was going to ask, the book's difficulty isn't a problem.
Well, yeah, it's a problem. It's an open problem.
Do we consider any code or just LDPC code?
So when we consider LDPC codes, so basically we consider codes of which the constraints are local.
And would you be happy, like this short code on 4D hyperbolic manifold, which is, sort of it has something like your local testability as long as the defect is not too big. Like as long as the distance to a code word is small.
Yeah, I think it's already interesting for small deltas which are constant. Okay,
Not for delta, which is sub-constant. Okay.
Yeah. Okay, so let me say first of all that this is really there are more open questions here than known than things that we really know. Okay, but these things sort of raise the question of, are there inherently quantum limitations on quantum local testability, quantum locally testable codes? Yeah.
If we forget about the LDPC requirement and we just consider a random CSS code, is that locally testable? Or I guess
But a random CSS code you need to have local tests for it to be locally
You don't just
testable.
require a few stabilizers, but each stabilizer
Yeah.
has to be testable.
Okay, so let's just see what happens. So in order to understand what's going on in the quantum case, let's just see what happens in the classical case. So first of all, how are we doing on time? I'm sort of.
Oh, let's see. Yeah, but you had quite a few questions, so 15 minutes.
Okay. Wait, when did we start?
Too late.
At 3:40, right? Okay, so let's just see what happens in the classical case. So first of all, classical locally testable codes on lattices don't exist. Why? Because, well, at least assuming linear distance. Why? Here's a very simple argument. Suppose you have a code with two words, S1 and S2, with distance d, and d is linear. Then just find a line like this that cuts, say, d over 3 of the errors on one side. At least d over 3, but not more than d over 2. You can do that. And then switch S2, if this is the values of S1, switch the values of S1 to the values of S2 here. So basically, all constraints here will be satisfied, all constraints here will be satisfied, only constraints will be valid are along the line, so it's very few, but the distance of the word will be large. So on lattices it won't work. And in fact, I don't know that this argument works in the quantum case. Okay, now on the other hand, on expanders, it's very easy to come up with locally testable codes using lossless expanders. Random codes will be locally testable. Basically, because all constraints, if it's a good expander, then all constraints sort of touch the error. Would touch the error only in one place if the error is not too dense. And think of parity check operations. If they touch the error only in one place, they will be validated. So the number of violations will be very large if it's expanding. Okay, so this is the picture in the classical case, and it seems that the picture in the quantum case is very different. Okay, what we know how to show is this is a result with Lior, who's sitting here. Is there are two results basically. One is that when the code is set on a good expander, it's a bad locally testable code. So let me say it more precisely. And this works for stabilizer codes only. For stabilizer codes set on epsilon local expanders, I'll explain that in a moment, then if you're looking at distances delta, which are small, these are the deltas, constant deltas which are small, so that these are the regimes in which it's actually easy to come up with classical locally testable codes, then the energy is small, meaning that the energy is O of epsilon, meaning that it's a bad locally testable code. So what does epsilon local means? It means that if you're looking at smalls, so this is a graph in which we put the qubits here and the constraints here, and we connect the qubit to a constraint it participates in. Then we say it's epsilon local expander if the number of constraints here on which a small set, a constant size set touches, is almost optimal. Meaning it's larger than the size of the set times the degree of each point here times 1 minus epsilon. So this means it's epsilon close to optimal. So if epsilon is small, it sort of spreads like the tree that Matt was talking about. If epsilon is 0, it spreads completely. If epsilon is very small, it almost spreads optimally. And if this is the graph, the underlying graph, then you can't have local testability. So why is that? Okay, so this is reminiscent of the results of Aharonov and Brandau, that somehow hardness in the quantum case is not supported by expanders in some funny way. The better the expanders, the worse the hardness. So this is also a result of me and Lior in the context of approximating QMA on expanders. It becomes easy, and here too we see the same phenomena that expanders makes things sort of, I don't know. They create some difficulty in creating. So okay, I'm not sure exactly about the connection, but it looks like a very similar phenomenon. So why is this true? Okay, I'm not sure I want to get into the detail of the argument. Okay, I'll say it. Yeah.
But just one thing. If big epsilon equals 1/4, not going to 0, then you get a beautiful expander, which we love to construct classically. And theorem won't say anything bad about it.
Right. So this is a weak bound on the theorem. I mean, you can always take epsilon to infinity, and there are as large as you want, constant. But the point is that classical codes exist with energy going almost to its optimal value. So this is a strictly quantum behavior.
But I guess you could say there's a giant gulf in the middle. Like if it's a really, really good expander, or if it's a really, really bad expander, then it won't work. But there's a very big middle region then.
Right, yeah, completely. Okay, so the proof idea, I don't want to go into the details of this, but basically it comes from the fact that, well, we're going to construct an error which has large distance but low energy. How? Take a stabilizer, and then we're going to define the error to be one of the operators in the stabilizer. Let's just look at an error at one location. Later we can spread the errors at faraway locations. So pick an error at one location, and since it comes from a stabilizer, well, there are two things to note. One is that since we're talking about stabilizer codes, stabilizer commute. So if I want this error to violate another stabilizer, it needs to not commute with it. But that stabilizer commutes with the original stabilizer. So what this means is that for a stabilizer to be violated by this error, it needs to intersect the original stabilizer in two locations. And the point is that with such expanders, such intersections of size 2 are rare. Okay, so maybe even if you didn't understand the exact details, it doesn't really matter. The point is that intersections of stabilizers, where the intersections are size 2, are rare in expanders. And this is the only way you can get violations. Okay, so then you can actually get not only a bound on expanders, but a bound on the robustness for any quantum locally testable codes, regardless of the graph. by combining the fact that it's bad on expanders because of the previous theorem, and it's also bad on non-expanders. And this is trivial for classical case. It's not trivial at all. At least we don't know how to do it trivially for the quantum case. If it's non-expansion, if the expansion is bad, then obviously it's the number of constraints that it touches is small. So you won't have local testability. But quantumly, you'll have to somehow make sure that the error that you start with has a large weight, that it does not reduce modulo the code. So you can do this, and you have some bound on any block. But this bound is weak. It just says that you can't get to optimum. Okay, so there are lots and lots of questions about locally testable codes. Okay, does this mean that, Greg's question, is there an open question here? Yes, we don't know of locally testable codes. So come up with a locally testable code which has, say, linear distance and energy which is constant even for any range of deltas. Do they exist on a lattice? We don't know. Perhaps similar methods that we use to bound locally testable codes can be used to deal with energy barriers and self-correction? I don't know. Now, and a very interesting question is how are they related to NLTSs? So the NLTS that Matt talked about, it seems that they're tightly related to them. It seems, this is really hand-waving, it seems that if you have a quantum locally testable code, you also have an NLTS. Reminding you what NLTS means, it means that you have a Hamiltonian such that all the low energy states are highly entangled. So why would you have such a thing if you have a quantum locally testable code? Well, imagine you have a trivial state, then it should be true that it's far from the locally testable codes. That's what we don't know how to show. If you have a trivial state, then it's far from the code. Now, if it's far, then by the nature of local testability, it also have high energy. Okay, so we don't know how to show that. And the question of relation to quantum PCP is of course, extremely interesting, but also extremely open. So in quantum PCP, in classical PCP, there are two basic notions that are very tightly related to local testability. One is local correctability, which is, suppose this is your string, and suppose this point is aired. Now I want to correct it by referring to two other random points which with hyperbolity are not aired. Then classically you can do it. If a particular point has an error, you can use the other point by choosing them randomly and correct it. Can you do it quantumly? Can you even define quantum self-correctability, quantum local correctability in this way? It's not clear that you cannot. No, I think it's an interesting question. And then local decodability. So another thing that seems to be essential in PCPs is the notion of this is supposedly the string that you encode, and this is the encoding string. And local decodability means that you can look at a small number of points, and then you can decode one bit in the string that you encoded. Okay? Quantumly, it's impossible to have this, right? Because quantumly, we know that if the code has a large distance, you will not be able to decode a bit to get any information locally. So you can't have local decodability, but possibly you can have local correctability. So it's not clear how. First of all, it's not clear to me, and also maybe to Guy, that local decodability is even essential in the classical world. And it's not, so the relation to PCP is completely open. Now, I don't know, how much time do I have?
Well, I think not too long. Or using 0.
Oh, 0. So 0 meaning -1, or do I?
I don't know whether you want to start a whole.
Well, I wanted to sort of browse through the connection to classical testability. So I think 5 more minutes would do it, but maybe, I mean, we can also skip it.
Are people up for it? Okay, let's do it.
Okay, you're actually,
Yeah,
I take it back
I'm a
what I said
bad
before
champ.
about being.
Okay.
Okay, so okay, so now we've asked about testing quantum properties. The question is, what happens when we test classical properties, classical strings to understand quantum properties? So before we were talking about testing quantum states. Now we want to talk about the possibility of testing classical strings locally to infer something about the quantum properties encoded by those strings. And the connection between those two notions is a completely open thing, I think. We don't understand the connection between the local testability in the classical case and the local testability in the quantum case when you encode quantum properties. So let me explain.
What does it mean to encode quantum properties?
Yeah, I also don't know.
Yeah. So suppose here's an example. Suppose we want to test that the ground energy of a given Hamiltonian is 0 and not, say, larger than 1/Pauli. If someone is giving to us some kind of a proof, but it's a classical proof. Okay? And we want to do this by probing only a small part of the proof. So that would be an instance of classical encoding. You get local probing, and you want to infer something which is a quantum property. Okay, so if the proof is a quantum state, then that would be equivalent to a quantum PCP thing, if you could do that. But now suppose the proof is a classical string, and we allow it to be exponential. So intuitively, it would maybe at the first attempt, I mean, the first thing that you would say is, okay, that's obviously possible because just take an exponential description of the quantum ground state. But we don't know how to probe it locally to get any information about it, because even just measuring 1 qubit is sort of spread over the entire string. So the question is, how can you actually have such an exponential proof which you could probe locally? And this is a very beautiful idea very beautiful connection from computer science, connects this question to something that seems very remote, which is the notion of interactive proofs, in which you have a verifier, which is a classical BPP machine, and a prover, which is possibly very powerful, and that prover wants to prove to the verifier something, such that if the verifier, if the something is correct, the verifier will accept with high probability. If the something is incorrect, it will reject with high probability. And it turns out that if you have such an interactive proof like this, for this property that the ground state, the ground energy is 0, then you accept, the ground energy is large, then you reject. If you have such an interactive proof, you could actually translate it to a string of exponential length by basically writing down all possible answers of the prover, all possible interactions. And that long string, basically, through the interaction, is only probed, because the interaction is only polynomial, is only probed at polynomially many locations. Okay, so that can be viewed as a local encoding, as an encoding of the property in such a way which is accessible locally. Okay? And well, such a thing is known to exist. We know that QMA is in IP by QMA is in P-space, and P-space is equal to IP, the class of problems that can be proven in this way. P-space is the class of problems that can be proven, can be solved in polynomial space. So this has been known. But the proof, first of all, this proof is extremely complicated. It's, it's conceptually complicated, and and this was one of the pillars that led to the PCP theorem. So I think it would be it is an interesting question to try to understand how this looks. without going through this proof, or trying to understand how this looks in a more quantum language. And this was done in our joint paper with Thomas and Itai, in which we provide something like a quantum sum check, which does this thing in a way which is sort of quantum, and well, I don't have time to go through the proof, but essentially it goes something like, well, the problem that you have to do in order to do this is to decide whether the trace of this operator is large or small. Turns out to be suffice to do that. If you know how to do that, then you know how to solve a cube. You know how to distinguish between eigenvalue 0 and eigenvalue 1 over poly. And in order to do that, well, you need to find an interactive proof for the trace. You need to allow the prover to convince you that the trace is something without being able to cheat. And essentially it's done by providing a protocol such that the prover needs to be consistent all the time with its previous answers. So the verifier is interrogating the prover, and the prover needs to answer and needs to be consistent all the time with the previous answers. And the actual protocol, which I'll be happy to explain later, is the following. You have a huge matrix. You want the prover to convince you that the trace of this matrix is something. He tells you some value. Then you ask him to give you the reduced density matrix of the first qubit. Exactly. And this is sort of the prover, this is exactly equivalent to the prover committing to the values of the trace of the original matrix, conditioned that the first qubit is in some state, but he's committing to the trace for all possible states. So by providing the reduced density matrix of one qubit, he's committing to the value of the trace for all possible restrictions of the first qubit. And then the verifier sends him a request. Now give me the trace of the restriction of the entire matrix to the first qubit being 1. And the verifier checks consistency and so on. And then if the prover cheats, then he gets at some point caught, because the problem becomes simpler and simpler and simpler until we get to the point where the verifier just needs to compute things like that, which are, well, not easy to compute, but we can do something with it, never mind. And let me just end with the fact that I think that understanding this kind of classical encodings are very, or how quantum properties are encoded in this, I think it's a very interesting question. And in particular, one way to understand this is to ask whether it's possible to provide such proofs for using provers which are weaker. Like if I allow the prover to be only QMA instead of being able to compute a p-space complete problem, would it be possible? So probably the weakest problem, open problem that I can, the easiest problem I can pose here is, can a QMA prover prove to a classical verifier a BQP problem? And that's related also, that goes back to what I started with, that's related also to the open question that was mentioned a lot in the previous conference, which is, can we have a verifier which is BPP and a prover which is BQP that has a quantum computer, such that the prover with a quantum computer, think D-Wave, can convince us that what they're doing is really solving a BQP problem by only classical interaction. So let me end.
Are there any questions right now?
Okay, I want to ask you a question I asked you earlier, but now that I heard the proof in more detail, I want to re-ask it, which is that proof you gave for this interactive proof to test QMA is basically a path integral you're figuring out an interactive proof for. And I don't see where you used that the transformations in the path integral were coming from were just coming from some Hermitian Hamiltonian, and that you hadn't inserted some extra projectors on intermediate time steps or made the Hamiltonian dependent upon the time slice. So wouldn't this also be an alternate proof that IP equals P space?
I think it would. I don't know how to interpret that, but I think it is true.
I also wanted to say that it's actually very similar to the original IP equals P space proof.
It's similar.
You also do this summation, so it has the same flavor as
Right.
the original.
Of course, it has the same flavor. The idea of the original, the brilliant idea of the original IP equals P space proof is really that you add redundancy, and so that somehow, if the prover committed to some value, then the verifier can ask many questions, and for the answers for these questions to be consistent with the previous answer that the prover gave, well, most of them cannot be both consistent and correct. They need also to be wrong. And so if the prover was claiming a wrong claim, he sort of pushed to claiming a wrong claim in the next step. And the only difference between what I showed and the original proof is in the type of redundancy. So in the original proof, the redundancy was done by polynomials of low degree. And so this is sort of the values of the different polynomial at different locations. But here, the different values here is sort of the redundancy is given by projection on different states, different directions, so a random direction of a qubit. So it's sort of it's very similar in that this structure is followed, but the tensor product structure is new. I mean, it appears there. I don't know if it's helpful or not, but it's sort of more natural in the quantum setting.
So it seems that here, in the classical setting, you have to add this redundancy. It seems that here you don't add this. You don't need to add it. It's somehow already inside the.
Well, you do add it because actually, if you want to compute the trace, all you need is to compute the diagonals, right? You're asking about the diagonals, but here you're asking about different directions. So you're asking about summations in different directions. So you can think of this as redundancy. I actually so Matt's comment about the path integrals, I think maybe it's possible to combine this with polynomials over path integrals to get something more interesting here. I don't know. I don't know, but the point that Matt made was that that really this proof works not only for QMA, but it works for the entire
that's why
P space.
It's strange, because somehow it seems that here you don't really need to add this extra redundancy. So I need. Okay.
So I
think this is something that's better to do offline.
Yeah, maybe we
Okay.
should- Are there more questions? Yeah, maybe then we should just finish this session. Thanks.
Thanks.